In this most silent moment of the night, when the noise of the outside world leaves its place to an inner stillness, we are left alone with the most fundamental truth of our existence. Being conscious. That inner witness which, at this very moment, transforms these words into sound in your mind and assigns them a meaning. That sweet melancholy that fills you when you remember a memory. That vivid sensation created by the color red in your mind. The coolness of a breeze touching your skin. All these experiences are the most basic, most ordinary facts of life for us. Yet, behind these experiences lies the deepest, most challenging, and most dizzying mystery science has ever encountered. This is not just a question about how our brain works. It is the question of why we have an inner world, why there is a feeling of being me. If these kinds of serene journeys, exploring the deepest secrets of your mind and its mysterious connection to the universe, appeal to you, and if you haven't yet joined this quest of discovery, you might consider subscribing to our channel and liking this episode. Your support helps these silent inquiries reach more curious souls and helps us unwrap the secrets of existence together. Now, clear your mind of the noise of the external world and let us begin a silent journey toward your inner universe. At the center of this journey lies that mysterious organ we carry inside our skulls, weighing about 1.5 kilograms, the brain. For decades, neuroscience has made incredible progress in unlocking the secrets of this organ. We increasingly understand how this complex network, consisting of billions of neurons, processes information, stores memories, and controls our movements. Mapping these functional aspects of the brain is called the easy problem of science. Of course, this is a relative easiness. Behind it lies a massive scientific effort. However, the real mystery lies beyond this map. As famously named by philosopher David Chalmers, the hard problem of consciousness begins here. The problem is this: how is it that all that electrochemical activity in the brain, all those neural firings, turn into a subjective experience, a feeling? Why is all this complex information processing accompanied by an inner world? In other words, why are the lights on inside and why is there someone home? Why are we more than just a sophisticated biological robot that takes inputs and produces outputs but feels nothing and is aware of nothing inside? We know that when you see the color red, neurons in a specific region of your brain fire at a certain frequency. This is the easy problem. But why that firing feels like red to you is the hard problem itself. The traditional answer offered by classical neuroscience is that consciousness emerges as a byproduct of a neural network that has become sufficiently complex, just like a computer processor heating up. However, this analogy leaves the most fundamental question unanswered. When a processor heats up, it doesn't feel hot. Its temperature simply increases. Yet our brain does not just process information. It simultaneously lives the experience of that information. It is this unexplainable gap between experience and brain activity that has pushed some researchers to seek answers in an entirely different place beyond classical physics and known biology. They suggested that the key to this deepest secret might be hidden in the most fundamental, strangest, and most mysterious layer of the universe. That the answer might lie in the mind-bending rules of quantum mechanics, which govern the behavior of matter and energy at the smallest scales. If these researchers are right, then consciousness might not be a phenomenon trapped solely within our skulls. It could be a bridge where our minds are connected to the fundamental fabric of the universe in a way far deeper and more fundamental than we can imagine. And the foundations of this bridge might be vibrating with the whispers of the quantum right now, within the tiniest gaps inside your brain. For decades, the most basic and powerful explanation science offered for consciousness was based on an analogy. The brain is a biological computer. According to this analogy, our complex circuits of billions of neurons are the hardware of this computer. The experiences we gain and the information we learn throughout life constitute the software. Those instantaneous electrical firings between neuron synapses are the 1 south and 0 south in the processor of this computer. This model has been incredibly successful in explaining many mechanical aspects of the brain, such as information processing, learning, and problem solving. Thanks to this model, we understood how light signals from our eyes turn into an image, and how sound waves reaching our ears become meaningful words. This allowed us to understand the brain as a machine. But this is only half the picture. What is missing from this picture? The ghost in the machine. The computer analogy can perfectly explain what the brain does, but it cannot explain why it feels something. Consider the world's most advanced supercomputer. It can perform trillions of calculations in seconds. It can solve the most complex problems. But that computer does not feel victory when it wins a chess game. It does not feel regret when it makes a mistake. It is not aware of its own existence. It simply calculates. This is the greatest wall the classical neuroscience model encounters. If consciousness is merely the result of a sufficiently complex calculation, why don't we just calculate? Why is a subjective experience accompanied by these calculations? This is the very heart of the hard problem of consciousness. Theoretically, it is possible for all our neural activities and behaviors to occur without any inner experience. Just like a philosophical zombie, this zombie is indistinguishable from you from the outside. It talks, laughs, reacts, and performs complex tasks. The neurons in its brain fire exactly like yours, but inside, in that most intimate room of the mind, there is no one. It does not feel pain. It simply runs the avoid pain program. It doesn't know what color is. It just analyzes the wavelength of light. It doesn't experience love. It just exhibits behaviors associated with love. It is a sophisticated biological automaton. According to the classical model, there is no measurable difference between you and this philosophical zombie. So, where does that priceless thing that distinguishes you from a pure subjective experience, your inner world, come from? This is the deep, unexplainable gap between brain activity and subjective experience that classical science has failed to bridge. This gap led some brave thinkers to the conclusion that the answers cannot be in the known world. That is, the classical, predictable world of neurons. According to them, to search for the secret of consciousness, it was necessary to descend deeper into a realm where the fundamental building blocks of matter behave strangely and counterintuitively. If consciousness was not the product of a classical computer, then what was it? Perhaps the brain was not a computer, but a quantum instrument. Perhaps the feeling of being me did not arise from the simple firing of neurons. It was born from processes occurring within much smaller, more fundamental structures inside those neurons that transcend the laws of physics as we know them. This search forced them to leave the safe harbors of classical physics and set sail into the strangest and most fundamental waters of the universe, the quantum realm, because the rules of that realm carried the promise of building a bridge over that deep chasm between mind and matter, the deep gap where classical science, the model that sees the brain as a computer, could not explain the cause of consciousness. This gap became the birthplace of a new revolution, the quantum consciousness revolution. The researchers who started this revolution asked a bold question. What if the secret of consciousness is hidden not in the large-scale structures of the brain, but in the smallest possible scales within the molecular world inside neurons? What if that rich inner world of our mind is a script written not by classical physics, but by the strange and mind-boggling rules of quantum mechanics? Although this idea initially seemed like science fiction, it began to be supported by more and more evidence in laboratories around the world. To understand this new perspective, we must remember how counterintuitive the quantum world is to our instincts. In the macro world we live in, everything is definite and predictable. A ball is either here or there. It cannot exist in two options at the same time. However, in the quantum realm, particles can exist in multiple states simultaneously. This state is called superposition. Particles can remain instantaneously connected to each other, no matter how much distance is between them. This is entanglement. and particles can pass through barriers that should normally be impassable. This is called tunneling. These rules contradict our daily reality so much that for most of the 20th century, scientists assumed it was impossible for these delicate quantum effects to survive in the brain a warm, wet, and noisy environment. However, nature was much smarter than we thought. And the pioneers of this new revolution went in pursuit of nature's intelligence. At the center of their hypothesis were extremely small, hollow tubes found inside every neuron in our brain, microtubules. These structures had been known for decades. Their tasks were to provide structural support to neurons and transport materials within the cell. They were seen as the skeleton of the cell, a passive construction material. But the quantum consciousness theory suggested that these humble tubes might actually have a much more exotic function. What if these microtubules are not just the cell skeleton, but also the quantum stages where consciousness emerges? According to this theory, while you are processing these words right now, those tiny hollow tubes in your brain are vibrating at frequencies that, according to the laws of classical physics, should collapse instantly in a warm and wet environment. But somehow, they continue to maintain that quantum coherence without collapsing. And if this is true, it could be the key not only to understanding consciousness, but also to understanding how our minds are connected to the quantum fabric of the universe. This would mean that your mind is not just trapped inside your skull, but is potentially entangled with the quantum field underlying all of reality. This is no longer just philosophical speculation. Researchers at Wellesley College discovered that anesthesia works by disrupting precisely these quantum processes in Scientists at Trinity College Dublin have found the first clues that they may have detected quantum entanglement in living human brains. Evidence is accumulating slowly but steadily. Consciousness may operate according to much stranger principles than we imagined. This is a journey that takes us from the deepest mysteries of the mind to the strangest corners of physics, potentially changing our thoughts on what it means to be me forever. And the first step of this journey begins with the story of one of the most extraordinary partnerships in science. Every great scientific revolution usually begins with the meeting of unexpected minds in an unexpected place. The story of quantum consciousness theory is exactly like that. At the center of this story were two people who could not be more different from each other. On one side was Sir Roger Penrose, a mathematical physicist, a genius who contemplated the most fundamental laws of the universe in the hallowed halls of Oxford, worked with Einstein, and won a Nobel Prize for his work on black holes. His world was one of abstract equations, cosmological secrets, and the nature of time. He was looking at the largest scales of the universe. On the other side was Stuart Hameroff, an anesthesiologist. His world was the concrete reality of operating rooms. His days were spent safely putting patients into a state of unconsciousness, and then bringing them back to the conscious world. His question was not as cosmic as but it was just as deep. Exactly what did those simple molecules of anesthetic gases do to the brain that they could completely eliminate that priceless feeling of being me, even for a moment? He faced the most practical, most tangible mystery of consciousness every day. The paths of these two minds crossed in the 1990s when they realized they shared the same fundamental frustration. Neither was satisfied with the classical answers offered by their own fields. Penrose saw that even the most advanced computers could not mimic the creativity and understanding of the human mind. To him, consciousness could not be the result of a simple algorithm or a series of calculations. There had to be a more fundamental and non-computable process behind it that classical physics could not explain. On the other hand, found the traditional explanation that anesthesia worked simply by slowing down the firing of neurons to be insufficient, because some anesthetic gases could completely shut down consciousness without significantly affecting neural firing. The secret had to be elsewhere. Their suspicion pointed in the same direction. The answer was in quantum mechanics. Penrose believed that the emergence of consciousness must be connected to a process involving the collapse of quantum states. Hameroff was looking for a biological stage where these quantum processes could occur, and he found that stage in his own field, anesthesiology and cell biology. Within the neurons, those tiny skeletal structures together, they developed a radical theory called ORCHR, or orchestrated objective reduction. This was a perfect union of two different worlds: Penrose's cosmological and mathematical genius, and Hameroff's biological and practical knowledge merged into a single bold claim. This claim challenged scientific assumptions held for years. According to them, consciousness was born not in the large and noisy power plants of neurons, but in the quiet, orderly, and incredibly small quantum stages inside neurons to microtubules. It was an extraordinary partnership between an anesthesiologist and a theoretical physicist. While one studied how consciousness was turned off, the other investigated how the most fundamental laws of the universe worked. And at the intersection of these two different perspectives, one of the most revolutionary ideas in science emerged. This idea suggested that the brain was not just a biological computer, but also a sensitive quantum instrument that resonates with the most fundamental vibrations of the universe. Penrose and Hameroff's extraordinary partnership drew a brand new route to seek the secret of consciousness. This route passed not through the large-scale neural networks of the brain, but through the molecular world inside each neuron. At the center of their theory was a structure that cell biology had known for a long time, but whose true potential it had never guessed: microtube. We can think of these structures as a network of extremely small, hollow protein tubes filling the inside of each neuron. Traditionally, the task of these tubes was to give the cell its shape and provide a kind of highway system for moving molecules from one place to another within the cell. They were seen as the hard-working but not so interesting laborers of the cell. However, Penrose and Hameroff suggested that beneath the surface of these microscopic highways, something much deeper and much stranger was taking place. To them, these tubes were not just a passive skeleton. They were the quantum computers of the brain. This idea was as elegant as it was surprising. The structure of microtubules offered an almost perfect environment for quantum calculations. They had a regular, crystal-like structure, and the hollow space inside provided some insulation from the noise of the outside world. This could be a protected sanctuary where delicate quantum processes could occur. So, how exactly did these quantum computers work? According to the theory, the proteins called tubulin that make up the microtubules could act as a quantum bit, or qubit, while a normal computer bit can take a value of either 0 or 1. A qubit, thanks to the famous quantum principle of superposition, could exist in both 0 and 1 states at the same time. This meant that even a single qubit could carry much more information. Hameroff and Penrose claimed that thousands of tubulin proteins within the neuron could enter this state of quantum superposition and perform calculations so complex and massive that a classical computer could not even imagine. This presented a brand new picture of how consciousness arises. According to this picture, consciousness was not just a product of the brain. At the same time, it was a dizzying idea, implying a relationship with the most fundamental fabric of the universe, the geometry of space-time. Each momentary awareness of our mind was actually an instantaneous meeting with the fundamental laws of the universe. Microtubules were the sacred places where this meeting occurred. However, this beautiful and poetic theory was about to hit one of the toughest walls in the scientific world. This wall consisted of a single question: how could all this delicate quantum dance survive in the warm, wet, and chaotic environment of a brain at body temperature? Penrose and Hameroff's ORCHR theory built an elegant bridge between mind and universe. The idea that microtubules worked like quantum computers, and that every moment of consciousness was a meeting with the fundamental fabric of the universe, was both philosophically satisfying and poetic. However, science does not progress only with poetic ideas. Even the most beautiful theories must pass the brutal tests of reality. And the biggest test facing the or theory was one of the most fundamental rules of physics. This obstacle is known as decoherence, and it is the wall that the idea of quantum consciousness has struggled most to overcome for decades. To understand the concept of we can think of a quantum state like a perfectly calm ripple on the surface of water. This ripple, the state of superposition, requires absolute isolation to maintain its existence. Even the slightest noise from the world around it, the impact of a temperature molecule, the touch of a light photon causes that perfect ripple to instantly dissipate or collapse. The magical uncertainty of the quantum world disappears, and the particle is reduced to the classical, single, and concrete state we know. This is why sensitive systems like quantum computers are operated in absolute isolation from the outside world and at temperatures close to absolute zero, 273 degrees Celsius, to protect those perfect ripples. Now let's compare this fact with the human brain. The brain is the exact opposite of a quantum computer lab. It is not cold and isolated. On the contrary, it is at a temperature of about 37 degrees Celsius, as hot as an oven for the quantum world. It is not dry and orderly. It is a watery and chaotic environment where billions of molecules are constantly in motion. It is not quiet. It is an incredibly noisy place, overflowing with countless chemical reactions and electrical signals occurring every moment. This is why, when the Orker theory was first proposed, a large part of the scientific community criticized it fiercely. The critics' argument was simple and powerful. It was impossible for those delicate quantum superposition states imagined by Penrose and Hameroff to survive long enough to perform meaningful calculations in the warm, wet, and noisy environment of the brain. According to physicists' calculations, a quantum state inside a microtubule should collapse within femtoseconds, that is, at an unimaginable speed like 1/4,000,000th of a second, due to the thermal vibrations of the molecules around it. This duration was not enough to make even a single meaningful transaction, let alone form a thought. This was almost a fatal blow to the theory. The idea of quantum consciousness began to be seen as a beautiful fantasy. It was shelved as a marginal speculation rather than a scientific reality. The brain was a garden too chaotic for quantum processes to flourish. If the secret of consciousness was to be sought anywhere, it should be sought not in this garden, but in the more classical and predictable world of neurons. This criticism hung over the theory like a dark cloud for decades. But just as this idea was about to fade into history as a scientific footnote, surprising news began to arrive from an entirely different field. Biologists, while studying nature itself, were finding evidence that the strange rules of quantum mechanics were operating in some of life's most fundamental processes, that it seemed that nature had already found a way to do the impossible, to protect and even use quantum effects in warm and wet environments. And these discoveries were the first sparks of a revolution that would breathe life back into the quantum consciousness theory, transforming it from a speculation into a testable, scientific hypothesis. The quantum consciousness theory had hit a wall against the warm, wet, and noisy environment of the brain. Even the most elegant ideas could be helpless against the brutal facts of physics. The theory remained in the shadow of the criticism of decoherence, the idea that quantum states must break down instantly, for decades. For much of the scientific world, this was the end of the story. The brain was not a suitable stage for quantum games. However, science sometimes finds its greatest answers in the most unexpected places, and the evidence to save the quantum consciousness theory from that dark corner would not come from physicists or neuroscientists working on consciousness. That evidence would come from biologists studying the most fundamental, most primitive processes of life. The name of this new era was quantum biology. At first, this might sound like a combination of two contradictory words: the abstract, fundamental world of quantum, and the complex living world of biology. However, as researchers studied life more deeply, they faced a surprising truth. Nature had transformed into a master quantum engineer over billions of years of evolution. It had already learned to do what we strive so hard to achieve in laboratories: to protect quantum effects in warm and wet environments, and even use them to its own advantage. This discovery changed everything. Now the question was no longer, can quantum effects exist in the brain? The question was, if nature utilizes the power of quantum mechanics even in the most basic processes to survive, why wouldn't it do the same for its most complex and mysterious creation, consciousness? This was like putting dynamite under the biggest criticism directed at the quantum consciousness theory. Perhaps the brain being warm, wet, and noisy was not an obstacle, but on the contrary, a specially designed condition for quantum processes to function. So, how did nature achieve this? Research showed that living systems developed clever strategies to protect quantum states from environmental noise. Sometimes, specific molecular structures acted as insulation chambers, creating protected pockets where delicate quantum processes could occur. Other times, it was even stranger. Sometimes nature used those environmental vibrations we see as noise, not as an enemy, but as an ally. These vibrations could create a kind of resonance that helped quantum effects persist longer. This new understanding allowed us to look at biology with completely fresh eyes. Living organisms were no longer seen merely as a sum of chemical reactions. They were hybrid systems where both classical and quantum laws were intertwined. And this quantum layer ensured that life was more efficient, smarter, and more mysterious than we thought. The quantum consciousness theory was no longer an isolated claim standing alone. It was part of a much larger picture beginning to be discovered in every corner of life: the quantum biology revolution. The most striking evidence of this revolution lay in processes we witness every day. But never think of the secret behind in those green leaves that are the energy source for almost all life on our planet. And in the instincts of those migratory birds that travel thousands of kilometers in the sky. Nature used the strangest principles of quantum mechanics so skillfully in these processes that the possibility that the brain might hide a similar secret became too strong to ignore. Now we will set out on a silent journey toward these most concrete and awe-inspiring examples of nature's quantum mastery. Strong evidence that nature uses quantum mechanics is found in a very familiar place: the green leaf of a tree. Photosynthesis. We have known this process since school. Plants use sunlight and convert it into the chemical energy necessary for life. Classical biology has been explaining the basic steps of this process for decades. A light particle of photon coming from the sun hits a chlorophyll molecule in the leaf. With this impact, an electron is released. The released electron travels through a series of molecules and reaches a biological factory called the reaction center. Energy production begins here. This story seems quite simple at first glance. But behind this simplicity was a deep conundrum that occupied scientists' minds for a long time. The process of photosynthesis is surprisingly efficient. Almost all the energy created by photons reaching the leaf is transported to the reaction center without any loss. This did not seem possible according to the rules of classical physics, because the electron does not have a single path to follow to reach its target. There are countless different molecular pathways in front of it, like a labyrinth. If the electron had behaved like a classical particle and chosen a random route by trial and error, it would have lost most of its energy along the way. It wouldn't be expected to reach such high efficiency. So, how did plants overcome this challenge? The answer lay in one of the fundamental principles of quantum mechanics: superposition. Researchers discovered that the electron released the moment the photon hits the leaf does not behave like a classical particle. Instead of choosing a single path, the electron explores all possible paths simultaneously. Thanks to quantum superposition, it transforms into a ghost-like wave and passes through every corridor of that molecular labyrinth at the same time. This way, it finds the most efficient and fastest route instantly and reaches its goal. This was a perfect optimization of nature and was possible entirely thanks to quantum mechanics. This discovery was a turning point for quantum biology. For the first time, it was proven that quantum effects not only existed within a warm and wet biological system, but also played a critical role in the continuation of life. The leaf had developed a mechanism to protect the ghost-like superposition state of the electron from external noise. This was concrete evidence that the argument that quantum states must instantly collapse in warm environments had long been overcome by nature. This situation was a powerful answer to the criticisms directed at the quantum consciousness theory. If a plant leaf could use the delicate principles of quantum mechanics for a basic task like increasing energy efficiency, why would it be impossible for the human brain, the most complex product of evolution, to use the same tools to create a mysterious phenomenon like consciousness? Perhaps the warm, wet, and noisy environment of the brain was not an obstacle, but, as in photosynthesis, a reactor specially designed for quantum effects to work efficiently. This quantum secret of photosynthesis made it difficult to see the quantum consciousness theory as a fantasy anymore. Nature had already opened the doors of the quantum world. It would be understood that not only electrons but also much more complex secrets passed through this door. Just as migratory birds making their flawless journeys of thousands of kilometers in the sky find their way using one of the strangest connections in the universe, photosynthesis showed us that nature has opened the doors of the quantum world. But this was not a single example. Nature used these strange rules in much more dynamic and complex areas of life as well. For another proof of this genius, we must look at the migratory birds traveling on those invisible highways of the sky. Every year we witness the flawless journeys of thousands of kilometers made by these small creatures. They cross continents and oceans and always reach their destination. So, how do they do this? Scientists have long known that birds use the sun and stars to find their way. But this did not explain the whole picture. Birds could find their way without getting lost, even on completely cloudy days or in pitch-dark nights. This showed that they possessed a sense we do not have, the ability to feel the Earth's magnetic field. This invisible force field, emanating from our planet's core, served as a kind of global roadmap for them. But how they read this map remained a great secret for many years. Initial theories suggested that there might be tiny iron particles in birds' beaks or brains that act like a compass needle. However, this explanation was insufficient to explain how refined this magnetic sense sensitivity was. They not only knew north and south, they could detect even very small changes in the inclination of the magnetic field. Such a sensitive measurement could not be made with a simple biological compass. The secret had to be deeper. At the quantum level, the key to this secret lies in one of the strangest concepts of quantum mechanics: entanglement. Entanglement is the connection of two particles as if by a cosmic bond. These particles, even if they go to two separate ends of the universe, do not break this mysterious bond. What happens to one is instantly felt by the other. No signal goes between them. No time passes. This is the instantaneous connection that even Einstein described as spooky. This idea had been a proven fact in laboratories for decades on subatomic particles. But no one had imagined that such a strange process could be working inside a bird's eye. According to the theory, the process works like this. A light photon from the sun hits a special protein in the bird's retina. This hit triggers a chemical reaction, and this reaction creates a pair of electrons connected to each other by quantum entanglement, called a radical pair. That's when the magic begins. These entangled electrons are affected by the Earth's magnetic field. The strength and direction of the magnetic field change the quantum properties of these electrons called spin. This change also affects the result of the chemical reaction they are in. And the result of this chemical reaction is sent to the bird's brain as a neural signal. This is the most striking part. The bird does not feel the magnetic field like a compass needle. It sees it as a pattern, a shadow overlaid on its normal vision. the lines of the magnetic field turn into a visual pattern for it. This way, it can determine not only its direction but also its latitude and longitude with incredible precision. It is as if it sees the magnetic map of the world with its eyes. This is a quantum process, even more complex than photosynthesis, and again, it works perfectly in a warm, wet, and noisy biological environment inside a bird's eye. Nature had once again solved the decoherence problem in an extremely elegant way. These two powerful examples, photosynthesis and bird navigation, had now almost completely refuted the fundamental argument of those who opposed the quantum consciousness theory. The argument that the brain is too warm and wet for quantum processes had now lost its validity. Nature was using the power of quantum. Now the evidence was directing us from these general secrets of nature to the most special mystery of the human brain, the secrets of anesthesia. And the first quantum whispers in a living brain were about to open the next act of this revolution. We have seen that nature uses the strange rules of quantum mechanics in its most fundamental life processes. The energy production of a leaf and the navigation of a bird made this fact undeniable. These discoveries removed the biggest obstacle to the quantum consciousness theory, the problem of the brain's warm and wet environment. Now the question was no longer, can there be quantum effects in the brain? The question was, can we observe these effects directly? With this question, researchers turned their attention once again to the heart of the theory, those tiny protein tubes inside neurons, microtubules. If Penrose and Hameroff's theory was correct, these microtubules had to be able to maintain quantum state superposition much longer than classical physics predicted. This was a testable claim, and in recent years, laboratories in different parts of the world designed clever experiments exactly to test this claim. The results were a turning point for the quantum consciousness theory. Researchers at the University of Alberta were among the pioneers of these experiments. They sent light onto microtubules isolated from neurons. Their goal was to measure how long this light could maintain quantum coherence when interacting with the microtubules. Quantum coherence is the ability of a system to remain in that magical state of superposition. Classical physics predicted that in the warm environment of the brain, this coherence should disappear almost instantly, in much less than nanoseconds. However, the results of the experiment surprised everyone. Microtubules could maintain quantum coherence for durations reaching nanoseconds. This duration may seem very short to you and me. However, on the scale of the quantum world, 1 nanosecond is almost an eternity. This duration was more than enough time for meaningful quantum calculations to be performed. In other words, it was experimentally shown for the first time that microtubules were durable enough to fulfill the quantum computer function required by the theory. This discovery was followed by another study conducted at the University of Central Florida. The results of this study were even more striking. Researchers found that under certain conditions, microtubules could maintain their quantum states for up to a second. This meant plenty of time not just for simple calculations, but for complex mental processes to influence neural activities. These findings proved that microtubules were no longer just passive structural elements. They were dynamic and mysterious structures where active quantum processes took place, as Penrose and Hameroff had suggested. These experiments had solidified a fundamental pillar of the theory. Yes, microtubules could play quantum games in the warm environment of the brain. This was a big step, but there was still a missing piece. How could we prove that these quantum activities had a direct relationship with consciousness? Just because there were quantum effects in microtubules did not mean these effects created consciousness. Perhaps these were byproducts of another biological function unrelated to our consciousness. At this point, evidence came from the most unexpected place. From Stuart Hameroff's own field of expertise, anesthesia research. These mysterious drugs that could reliably turn consciousness off and on carried the key that would allow us to find that missing link between quantum activities and subjective experience. And this key was about to unlock not a laboratory door, but the door of consciousness itself. It was now an experimental fact that microtubules could play quantum games in the warm environment of the brain. But did these games have a role on the mysterious stage of consciousness? The answer to this question was hidden in one of the most powerful tools used to understand the nature of consciousness. For decades, anesthesia. Anesthetic drugs are a miracle of modern medicine. When these simple molecules enter the brain, they reliably and temporarily eliminate that complex feeling of being me, the subjective experience. They can turn consciousness off and on like a light switch. If we can find exactly where this switch is connected, we can also find where consciousness itself is located. Traditional neuroscience assumed that anesthesia worked by affecting how neurons communicate with each other, the synapses. According to the theory, these drugs slow down the firing of neurons, interrupt the general flow of information in the brain, and thus consciousness disappears. This explanation was accepted for many years. However, there were some annoying anomalies that this model could not explain. For example, some anesthetic gases could completely shut down consciousness without much affecting neural firing, or even by increasing it. On the other hand, situations like epilepsy, seizures that created much larger electrical chaos in the brain did not always eliminate consciousness. The switch might not be where we thought it was. At this point, a study conducted at Wellesley College in 2024 changed everything. While examining the brains of mice under anesthesia, researchers made a revolutionary discovery. They found that anesthetic drugs did not just affect the firing patterns of neurons. Their real target was much deeper, in a much more fundamental place. These drugs were directly binding to microtubules and disrupting their quantum activities. Anesthesia was targeting not the large power plants of the brain, but the miniature quantum computers inside those power plants. This was an exciting finding in itself, but researchers went one step further. In the second stage of the experiment, they gave the mice another drug that stabilizes microtubules, that is, makes their quantum states more durable. Then they applied anesthesia to these mice. The result was breathtaking. It took significantly longer for the mice, whose microtubules were stabilized, to lose consciousness under anesthesia compared to normal mice. In other words, the more powerful you kept the quantum activities in the microtubules, the harder it became to shut down consciousness. This discovery was a revolution, because for the first time, a direct causal link was established between quantum processes in microtubules and our subjective experience of consciousness. This was no longer just a correlation. This was concrete evidence. If consciousness were a purely classical phenomenon, that is, if it consisted only of the firing of neurons, disrupting or strengthening quantum activities in microtubules, should have had no effect on consciousness. But it did, and it had a very clear effect. The results of this experiment confirmed one of the most fundamental claims of the quantum consciousness theory. Those orderly, coherent quantum activities within the microtubules were indeed necessary for conscious awareness. Anesthesia was eliminating consciousness not by turning off the brain's electrical grid, but by stopping the quantum generators that provide power to that grid. This was an idea that fundamentally shook our understanding of the nature of consciousness. And the consequences of this idea were not limited only to how we understand anesthesia. It was opening a door that could begin to explain some of the most mysterious aspects of the mind, even the connection between different consciousnesses. The secret of anesthesia led us to the quantum foundations of consciousness. Now we know that our awareness depends on the delicate quantum dance of those tiny microtubules inside neurons. But does this dance take place only inside a single neuron? Or do different regions of the brain play this quantum symphony together in a way we do not know? This question brings us to one of the strangest, most mysterious concepts of quantum mechanics, which even Einstein described as spooky: entanglement. Entanglement is the behavior of two or more particles as a single, unified system, no matter the distance between them. They are connected by an invisible bond. A measurement you make on one instantly affects the other. This idea had been a proven fact in laboratories for decades on subatomic particles, but no one thought that such a delicate and strange connection could exist on a macroscopic level in the warm and complex environment of the brain. However, recent experiments at Trinity College Dublin provided exciting clues pointing to exactly this mind-boggling possibility. Researchers used very complex MRI techniques to observe the quantum properties of protons in living human brains. And what they found was surprising. In the experiment, they detected some signals in certain regions of the brain, especially those known to be associated with consciousness, that they normally shouldn't see. These signals carried a signature that protons in different brain regions could be in quantum entanglement with each other. That is, particles in one part of the brain could be in an instantaneous connection with particles in another part of the brain, regardless of the distance. Although the interpretation of these results is still controversial, this was potentially the first evidence of quantum entanglement in a living biological system, the human brain. If these findings are confirmed, they would fundamentally change our understanding of consciousness. They could provide an elegant solution to one of the biggest problems that has puzzled neuroscientists for years: the binding problem. The binding problem is this: our brain processes different features of an object, its color, shape, sound, texture in different parts of the brain. So how is it that all this separately processed information comes together in our mind as a single, unified, and continuous experience? When you see a red ball, redness is processed in one place and roundness in another. Why do you perceive a single red ball instead of red and round separately? While classical neuroscience proposes models like the synchronization of different neural circuits to solve this question, these models are not fully satisfactory. However, quantum entanglement offers a much more fundamental solution to this problem. If different regions of your brain are entangled, then neural signals do not need to go from one place to another for information sharing. Sharing happens instantly. They are already part of a single unified quantum field. That is, you have a single red ball experience, because the momentary state of your brain is a single and indivisible quantum state. The consequences of this idea are not limited only to the inside of a single brain. If consciousness really involves quantum processes, then does that spooky instantaneous connection stay only within our skulls? This opens the door to the most radical and dizzying questions about the nature of consciousness. Now, consciousness might not be an isolated private phenomenon trapped only in individual brains. It could potentially be part of a massive, interconnected network of quantum information spanning the universe. Your thoughts, feelings, and experiences might not belong only to you. They could be entangled with the quantum structure of the universe in ways we are only beginning to understand. Different parts of our brain can communicate instantly via quantum entanglement. This idea could explain how consciousness works as a single whole. But does this spooky connection have to stop at the borders of our skull? This question leads us to one of the most radical possibilities of science. Perhaps consciousness is not an isolated phenomenon emerging in individual brains. Perhaps we are all connected to an invisible quantum information network spanning the universe. According to this view, each of us is like a node in this cosmic network. Our thoughts and feelings might not be solely the product of our own neurons. They might also be reflections of whispers coming from this universal field. This offers a potential explanation for many intuitive moments we dismiss as coincidence, like feeling the tension in the air when you walk into a room or someone you're thinking about calling you. Perhaps these are sparks where our consciousness momentarily enters into entanglement with the quantum fields of other minds. This also redefines the nature of human connection. Empathy, the ability to understand another's feelings, is perhaps not just imagining that person's situation in our mind. In moments of real empathy, we might be directly accessing another's quantum consciousness field. We might be directly feeling their pain or joy through entanglement. This implies that the sharp boundary between me and the other is actually quite fluid at the quantum level. Although these ideas are currently speculative, they have begun to be investigated scientifically. Researchers at the University of California are studying a phenomenon they call consciousness fields. Using sensitive devices, they detected synchronized quantum signatures in the brain activities of people standing close to each other. This is one of the first concrete clues that human consciousness might extend beyond the physical boundaries of the body. If such a cosmic network really exists, it makes us question not only the connection between humans but also the relationship between life and inanimate matter. This is like a new chapter written in the language of modern science for the idea of the unity of everything, expressed by different philosophical traditions for thousands of years. Now, these ideas are transforming from just beliefs into testable hypotheses. This new perspective leads us to some of the most fundamental questions of being human. For example, free will. If everything is determined by the laws of classical physics, then our choices are also just an illusion. However, quantum mechanics offers true uncertainty and probability at the fundamental level. Perhaps our free will originates from exactly this quantum uncertainty. And if our consciousness is connected to this cosmic network, then where do the boundaries of our identity begin and end? These questions are now some of the most exciting research areas, not only for philosophy but also for physics. The idea that our consciousness might be connected to a universal network blurs the boundaries of who we are. However, the potential impact of quantum mechanics on our mind makes us fundamentally question not just who we are, but what we do, that is, our choices. One of the greatest philosophical debates lasting hundreds of years is whether free will is real. If the universe works like a clockwork mechanism, as classical physics suggests, then every event is an inevitable result of the events preceding it.